Welcome to part 6 of the mini course Preparing for Organic Chemistry. We continue with isomers. Okay, so I'm kind of guessing that a lot of you are feeling like this image at this point. Yeah, the content has certainly taken a fairly steep turn to the more challenging and more complicated. And I'll tell you why you're having a headache. You're having a headache because the subject is very, very spatial. Now, we all have different degrees of spatial reasoning and spatial skills that we're born with, and those can be developed, right? Just like musical talent or artistic talent or mathematical talent. And the ability to see three-dimensional molecules in 3 dimensions in your brain is an important skill that you will develop to some extent. But that's what you're struggling with right now, especially the right-hand part of this chart in terms of stereoisomers and chiral carbon. Tetrahedral carbon is 3-dimensional. And so that is what's difficult, especially to illustrate this on a 2-dimensional surface, right? And again, I urge you to use your molecular model kits. If you haven't purchased one, then I will make some recommendations in the description to this video. But that will help you a great deal. But still, like with anything else that's new and different and strange and challenging, you're just going to have to drill and drill and drill, and you're going to have to make mistakes. And that's part of the learning process. All right, but I can help you in this video get to a better point in understanding isomers and developing these skills by doing a bunch of examples. Let's take a look at some examples. Okay, here's how this is going to work. You're going to examine each pair of structures on these slides, and you're going to conclude that the relationship is either none, there is no isomeric relationship, or they're identical molecules. And by the way, if you don't feel there's an isomeric relationship, okay, you're to write down in your notes an N. If you feel they're identical molecules, write down an I. If they're constitutional isomers, a C. Geometric isomers, a G. Absolute stereoisomers, an A. Relative stereoisomers, an R. Okay, got it? All right, so take a look at this and see what you conclude, and we're going to look at the answers in a moment. And here are the answers to these 3 problems. The first set of molecules have no isomeric relationship. They don't have the same molecular formula. The molecular formula of the molecule on the left would be C7H12, right? C7H12. The molecular formula of the molecule on the right is C7H14. No isomeric relationship. Okay, what about the middle pair? The middle pair are constitutional isomers. They have the same molecular formula, right, which we said was C6H12, right, but different connectivity. You've got to make and break bonds to different atoms to interconvert those 2 structures. Constitutional isomers. The same is true of the bottom pair. Same molecular formula, but you have to make and break bonds to different atoms to interconvert those 2 structures. Constitutional isomers. Okay, well, this is kind of fun. Let's try these. Right? So again, study the pairs of structures and denote them with, right? Denote them with N for no relationship, I for identical, C for constitutional, G for geometric, R for relative stereoisomers, A for absolute stereoisomers. Okay, so take your time, study the molecules, use your models, You have all the time you need. Here are the answers. The top pair have no isomeric relationship. In fact, they're identical molecules. So I have an N there, which is true, but I really should have an I. Those are identical molecules because all I've done is I've taken the structure on the left in the plane of the screen and I flipped it 180 degrees out of the plane back into the plane. I've flipped it so that that ethyl piece, that 2-carbon piece on the left in the left-hand structure, right, which is kind of pointing up, is now pointing down. Okay, but you can certainly superimpose both those structures on each other by reorienting them in space. A reorientation, okay, does not change the molecule. All right. What about the middle structures? That is also N, or really I should say I, for identical structures. They're identical structures. How is that possible? How is that possible? Because even though I've used stereo bonds to indicate the bonding to two of those carbons, and those are in fact tetrahedral carbons, they're sp3 carbons, all the carbons in this structure or structures are sp3, therefore they're tetrahedral, therefore you can use stereo bonds to depict, if you want, any of the tetrahedral carbons. That doesn't make them chiral carbons, and they're not chiral carbons because they don't have 4 different attachments. Okay, the carbon on the left, or C2 if you will, right, has 2 methyl groups, as does the carbon to the right of it. Carbon 3 also has 2 methyl groups. So I can depict the tetrahedral arrangement of the bonds and the attachments, but if you don't have 4 different attachments, there's no opportunity for stereoisomers. What about the structures on the bottom? Yes, those are absolute stereoisomers. And notice something. I inverted the configuration of both chiral carbons with the same orientation of the molecule, and that actually creates the non-superimposable mirror image. All right. Okay, we'll do one more set of these. One more set of these. All right. Again, take a look, study them, use your models. Okay, are they not isomeric? Are they identical? I know that's a little confusing. They go together. Are they constitutional? Are they geometric? Is it absolute stereoisomerism? Is it relative stereoisomerism? See what you think. Here are the answers. Now, the first set above is interesting. Okay. The answer is no or I, no N-I, right? Identical structures. Okay, because imagine taking the structure on the right and imagine that there's an axis of rotation that passes through the 2 methyl groups, and then rotate that molecule 180 degrees, and what do you get? You get the structure on the left. They are identical molecules. What's confusing is it looks like they possess chiral carbons with 4 different attachments. Okay. When in fact they don't. Look at the middle set. The middle set are relative stereoisomers because you can rotate that second structure through those methyls all day long and you're never going to generate the structure on the left. Or to put it another way, the methyls on that 6-membered ring are closer together in the left-hand structure, which we call cis, than they are in the right-hand structure, which we call trans. Those are relative stereoisomers, and notice that the configuration of only one of the 2 chiral carbons has been reversed. Okay. What about the last set on the bottom? Those are identical The answer is N or I, identical molecules. All I did was I did a carbon-carbon bond rotation around C3, C4, right? If the carbon bearing the hydroxyl group is C2, then I did a rotation about C3, C4. That's a single bond. I can rotate about a single bond, and that puts that group on the left with the hydroxyl up. If you rotate by 180 degrees, you get the structure on the right. It's a reorientation. It's a rotation or reorientation. A rotation, a bond rotation, a single bond rotation, or a reorientation, if illustrated and depicted properly, does not generate an isomer. Okay, so I'm going to end this video here. I don't expect that you have mastered isomers, especially stereoisomers. I mean, goodness, take a look at your textbook if you have your textbook already. If you have a textbook, take a look at it, and you'll see that stereoisomers and chirality are an entire chapter or chapters. So it's a big, big, big deal, and there's a lot to it. No, the idea here is, again, to introduce you to isomers, make you aware of a few things, so that, again, when you go into this in more detail in your organic course, you're not shocked. You've seen it before. At least you've been introduced to it. Okay?